Section 4.3, Applications of Systems. In this section we're now going to take a look at word problems that require us to set up the systems of equations that we've been solving in the previous two sections of 4.1 and 4.2. Some of the problems will present a situation where we set up a two-variable system, similar to what we were dealing with in 4.1. And then some of the examples will result in a situation that requires a three-variable system, just like what we were dealing with in 4.2. So from the situation, you need to come up with the equation and determine if it's going to be a two-variable equation system or three-variable. So we'll look at how to do that and how to common sense your way through all of these. So our first example, we have the perimeter of an NBA basketball court is 288 feet. Perimeter meaning the distance around the rectangular court. The length is 44 feet longer than the width. Find the dimensions of the court. Okay, so important things they give us here. They tell us the perimeter. So we're dealing with perimeter, and it's a rectangle, if you know anything about basketball. They give us the perimeter, 288 feet. So that's important because we are given since we are told that we're dealing with the perimeter, you want to use the perimeter of a rectangle formula in this problem. And then the other important piece of information we're given is that the length specifically is 44 feet longer than the width. So that means whatever the width is, the length is equal to that plus an additional 44 feet. So we need to set up equations that represent that. So first thing I usually like to do in some of these word problems, if possible, is draw a picture of what's going on. So if we have a basketball court here that is a rectangle shape, we'd have half court line down the middle, and then you'd have your 3-point line somewhere around here, and here. Alright, so as is the case with any rectangle, we have two lengths that are the same and two widths that are the same. We're told that the length is 44 feet longer, so we know the long side we're considering to be the length. So the top and bottom of this rectangle, those are the two lengths that are the same size, and then these are the two widths, how tall this rectangle is. Okay? So, as I was saying, the first piece of information we're going to need to know is that the perimeter is, the perimeter formula for any rectangle. We can find this by doubling your length, multiplying your length times 2 because you have two lengths that are the same, and then doubling your width because you have two widths that are the same, and then adding those two values together. That's how we find the perimeter of any rectangle. So there's our perimeter formula, but in a system we need a second formula, a second equation to deal with. But for now we can plug in what we do know. We do know that the perimeter is 288 feet, so we can replace that P with 288. We don't really know what the length or width is yet, specifically. We don't know the exact values. We just know some clues that are going to help us find it. So we have to keep this equation as 2L plus 2W. Okay, that's going to have to add up to 288. We know that. Well, now we have to use the other piece of information given to set up another equation. We know the length is 44 feet longer than the width. So I was saying this before, okay, the length is going to equal whatever the width is plus an additional 44 feet. So there's a second equation we can use. So now we have a system that has this equation and has this equation. And so I guess at this point it would be your job to determine what would be the easiest method to solve this system. because one of our equations has a variable already solved for, the second equation is solved for the length, it'd make it easier to use the substitution method, the first, or maybe the second method we learned. So I would suggest let's do that. Substitution. Okay. So what we learned in 4.1, after we graphed the first method we looked at. So substitution, remember, we take what the length is solved for, length is equal to w plus 4, and then we substitute it into the other equation wherever we see that length variable. So we're going to take w plus 4 and replace L with a w plus 4 in that first equation we came up with. Okay. So, doing that, we're going to have 288 equals 2 times our length. Well, our length we're replacing with w plus 44, then plus 2w that was already in the perimeter equation. Okay, so we just drop that piece down. Now that we've substituted that into the first equation, now we have an equation that's just involving the variable w. And now we can move some things around and solve for w. So we can take this, distribute the 2. Okay. That's going to give us 288 equals 2w plus 88 plus another 2w that was on the end of the problem. Combining like terms, the 2w and 2w, we can combine to get, excuse me, 4w. So 4w plus 88. We would then want to subtract 88 from both sides of this equation. Doing that is going to give us a 200 over here and a 4w on this side. And then dividing on both sides by 4, we'd end up getting that w equals 50 feet. And I say feet because it is going to be in feet. Since that's the unit we're dealing with in this problem. So our width we just found, 50 feet. So that's half of the problem. We have to find the other half to find the other dimension of the basketball court. So if we want to come up over here, well, we know the length is going to be equal to whatever the width was plus an additional 44. So it's going to equal, our width we just found out was 50 feet. Adding 44 to that is going to give us, the length equals 94 feet. Okay. So the width is 50 feet and the length is 94 feet. So there's our dimensions of our basketball court. Okay. And it just happened on that problem, substitution was the easiest method. It won't always be the case, but you have to determine that in each problem. Alright. Looking at our next example then. We have a situation involving the different prices of seats. So at a comedy club, you have VIP seats costing more than the regular seating. If 2 VIP seats and 1 regular seat cost you $113, but then if you were to just buy 1 VIP seat and 2 regular seats, that costs $97. How much is the price for each seat? So in a problem like this, whatever we're trying to find, that's what we want to use a variable to represent. Okay, so since we're trying to find how much is the price of each seat, we want to see how much a VIP seat is and how much a regular seat is. So I would suggest using the variables V for VIP. That's going to represent the cost of a VIP seat. And then we can use R to represent the cost of a regular seat. Okay. So using those two variables, we need to set up two equations. Well, look at what they tell us in the problem. We have two VIP seats plus one regular seat. That costs a total of $113. So from that we can set up the equation that 2V plus 1R, okay, for one regular seat, so two VIP seats plus one regular seat, or just R by itself, that's going to equal $113. Okay. And then one VIP seat plus two regular seats, that only cost $97. So from that we can set up the formula: a single VIP seat plus two regular seats, that's going to equal a total of $97. Okay. So with that problem, or now that we have the system set up, we want to look at this and determine which would be the best method to solve this system. You really could use any method, and we could do substitution like we did on the last problem. We would just have to either solve this bottom equation for V or solve this top equation for R, and then substitute into the other equation. However, because they are already, the V's are lined up, we have our R's lined up, and then our constants lined up, this is set up decently for elimination as well. So you kind of make the choice which one you would rather use. I'm going to go through doing this one using elimination. Okay. So in order to do elimination, we need either the V terms to equal each other or be opposites of each other, or we would need the R's to match each other exactly or be opposites. So what I think I'm going to do is I'm going to multiply this top equation by 2 to make this become a 2R, so then it matches the 2R in the bottom equation. Okay. So this gives us 4V plus 2R equals 226. And then we want to just keep the bottom equation as it was. V plus 2R equals 97. Okay. Now that we have the R terms matching, if we were to subtract, that would cancel out the R terms. So 4V minus 1V, 4V minus a single V, ends up giving us 3V, but subtracting the 2R minus a 2R cancel those out. So our result is 3V, nothing for the R terms anymore. 226 minus 97 gives us 129. Okay. And then that's a pretty easy equation for us to solve. I'm going to bring it up over here. V equals 129. Solve for V, divide by 3 on both sides. And finally we get that a VIP ticket would cost $43. Okay. So again, there's half of our answer. We then want to use that to find what is the cost of the regular seating. So we have to take that and use either equation 1 or equation 2 that we had set up, plug in 43 for V, and then find out what R would have to be. Doesn't really matter which equation you use. I guess I would just use this second equation. So we end up having V plus 2R equals 97. Replacing $43 in for V, we get that 43 plus 2R equals 97. We would then want to subtract 43 from both sides, giving us that 2R equals 54. So if 2 regular tickets would cost $54, dividing that by 2 on both sides, we get that a single regular ticket would cost $27. And there's the second part of our solution. So I think hopefully you're starting to see the kind of usefulness of systems. When we were just solving systems that were basic equations that had no meaning, we were finding an x and y value that was a solution. Well, now when we actually apply these systems to a real-world situation, you can see what we're finding is something that could actually be useful in the real world. And we could do some of these problems by graphing them, using x and y as our variables rather than something like V and R or something like P and L in the top situation. But I think it's probably easier just to do these algebraically, do them by hand rather than graph them. All right, we can flip to the next page, look at those examples. All right. Our first example is a mixture type of problem and situation we have. How many ounces each of a 5% hydrochloric acid mix and a 20% hydrochloric acid mix must be combined to get a 10-ounce solution that is 12.5% hydrochloric acid? All right, these problems are tricky. So what they're really asking us is how many ounces of the 5% mix do we need and how many ounces of the 20% mix do we need. So we want our variables to represent those two things. So how many ounces each? Well, we can use F to represent F for 5. I'm gonna use. So F is going to represent the number of ounces of the 5% acid mix. And then 20%, I'm going to use the variable T. That's going to represent the amount of ounces of the 20% mix. Okay. We know right off the bat we could set up one equation involving F and T because these two are the amount of ounces of both are combining to get a 10-ounce total solution. Okay, so combined to get a 10-ounce solution. Well, then we know F, the amount of ounces of 5%, plus T, the amount of ounces at 20%, has to equal 10. So right off the bat, we can set up that first equation. F plus T ounces plus those ounces have to give us 10. Okay. The next equation we want to set up has to incorporate the percentage of alcohol in each type of mixture. So this is the 5% ounces, this is the 10% ounces. We need to involve those percentages now. So all of our percentages, since we want to put them in an equation and you do operations on them, we need to convert these things to decimals. So the 5% hydrochloric mix, we want to convert that to a decimal, which would be 0.05. The 20% hydrochloric acid mix, we want to convert that to a decimal as well, 0.2, or if you want 0.20. To remind yourself that's the 20%. And then lastly, the 12.5% hydrochloric acid mix, that we can convert to a decimal, 0.125. Okay? So I guess the idea is that if we take the percentage and we multiply it by ounces, that gives us, I guess, the amount of alcohol in that specific mix. So our second equation is going to look like incorporating our percentages. 5%, 0.05, times the amount of ounces we have of that mixture, which F is representing the amount of ounces, plus 20%, 0.20, times the amount of ounces at 20%, which was T. That is going to equal 12.5%, 0.125, times the amount of ounces we have at 12.5%. Well, how many ounces do we have at 12.5%? That's going to be our final mixture. So we wanted at the end it to combine to get 10 ounces of 12.5% acid. So we're going to multiply this 12.5% times the amount of total ounces we want in the end, 10. Okay. So with our, I guess, equation, we can go ahead and multiply the 10 times 0.125. That is going to give us the same 0.05 F plus 0.20 T equals, well, we'd end up getting 1.25. Okay. Now in a problem like this, if we don't want to deal with decimals, we could convert this problem so that they'd all be whole numbers, because we want the decimal to move 2 places to the right in each of these cases to make them become whole numbers. We would need to multiply by 100, so we can do that. Let's clear our decimals. And to do that, again, we're going to multiply by 100. Okay. So when we multiply by 100, this becomes 5F plus 20T equals 125. That might be a little bit easier to work with. Alright, so now we want to look back at our 2 equations. We have F plus T equals 10, and now our new equation we just set over here. So let's re-look at these. F plus T equals 10, and 5F plus 20T equals 125. Okay. So once again, you have options. Because F and T in both equations are on the left-hand side, and the constants by itself on the right-hand side, this is set up decently for elimination. Of course, you could solve this top equation for either F or for T by getting the other variable on the other side and then doing substitution. I like I guess I'll just continue doing elimination since it's set up that way, and I'll save substitution for problems where we already have something solved for. So let's use elimination. Doing so, we need one of these variables to match, either the f's or the t's. It'd be a smaller value to make this 5f match this 5f, so we'd have to take this top equation and multiply by 5. So then we end up getting 5f plus 5t equals 50. Okay, from our first equation. Our second equation we want to keep as it was. 5f plus 20t equals 125. And now that those two equations match up, the f terms match each other, to cancel them we'd have to subtract. Okay. When you have the exact same terms, you subtract to cancel those out. So the f terms would cancel. 5 minus 20 would give us a negative 15t here, and then 50 minus 125 would give us a negative 75 here. Okay. Which we then can come over here and solve. Negative 15t equals negative 75. Divide on both sides by negative 15, and we get that t equals 5 ounces. And remember, t represented the amount of ounces at 20%. So 5 ounces of the 20% mix is how much we would need. But then back to our original equation, we know that the 2 ounces together has to add up to equal 10. So if we know that the amount of ounces of the 5% mixture plus the amount of ounces in the 10% or 20% mixture, t, equals 10, well, we can replace t with 5 now, because we know that there's 5 ounces of the 20% mixture. So subtracting 5 from both sides, we get that. We also would need 5 ounces at the 5% mix as well. So putting 5 ounces of the 20% mix, 5 ounces of the 5% mix is going to give us 10 total ounces at 12.5% mix. It's not always going to work out exactly that way. You can't just cut them in half. So if you were thinking that, don't try every problem like that. It's not usually going to work out perfectly 5 and 5 like it did in this one. We just got lucky it did on this one. Alright, I'll finish off this page, be done with this video. We've got our last example. Alright, now we have one of those famous car leaving from one area, another car leaving from another, when do they meet each other type of problem. Although this is dealing more with their speeds. So we have a car leaving Houston towards Dallas, traveling 15 miles per hour faster than a car driving from Dallas to Houston. If they meet after 1 hour and 30 minutes, and Houston to Dallas is a 300-mile drive, how fast are each traveling? Okay. So we know a couple things, but that's what we need to pull out. But most importantly, what are we trying to find? We're trying to find their speeds. How fast is the car that's coming from Houston traveling? How fast is the car coming from Dallas traveling? So that's the first and most important thing. We need to set a variable to represent these two things. So how about the car coming from Houston? We can use H. Okay. So H is going to be the speed of the car leaving Houston. And then we can use D to equal the speed of the car leaving Dallas. Okay. So we can then use those to come up with our equations, but in this problem, how are we even going to come up with an equation? Well, whenever you're involving something with speeds and distances and amount of time, we want to use a distance formula. Okay? So you'd have to just know this formula, which is that distance traveled is equal to your rate, okay, how quickly you're traveling, times time. How long have you been traveling? So in this case, when I say rate, it means speed. Okay, your rate is how fast you're traveling, how many miles per hour in this case. Okay. Yeah, in this case, because we're dealing in hours and we're dealing in miles, our rate would be miles per hour. So we want to use this to come up with two equations. However, before we even come up with the equations, it might be good to convert 1 hour and 30 minutes to a decimal, because 1 hour and 30 minutes is not 1.3 hours, which a lot of students end up making that mistake. Okay, 1 hour and 30 minutes, actually, to convert this to a decimal, it's going to be 1 point something, but you have to take the 30 minutes and see what portion of an hour is that. Well, 30 minutes out of a whole hour would be 60 minutes. So 30 divided by 60 is going to give you 0.5. So an hour and 30 minutes is actually 1.5 hours. Okay, so we're going to use that in our formulas. So we know distance traveled is equal to rate times time. So our Houston car the distance that it traveled is going to be equivalent to its rate, which we don't know yet, call H, times however long it was traveling. Well, we know both cars were traveling for 1.5. Okay. Yeah, since over here, 1 hour and 30 minutes. Okay, so we do know the time is 1.5 hours. The Dallas car distance, well, it's going to be equal to its rate. We don't know this yet. Remember, we're using D to find that. Times 1.5. Okay. Well, some things we do know. The total distance Okay, together between the two, if one car's leaving Houston, the other car's leaving Dallas, they meet somewhere in the middle. Either way, the total distance traveled between the two of them is going to be 300 miles. Okay, if one car's leaving Houston, the other car's over here in Dallas, even if the one car going faster ends up making it somewhere over here closer to Dallas before they meet, maybe it traveled 200 miles, that means the car coming from Dallas had to have traveled 100. And they're still together between the two are going to end up being traveled 300 miles. Even if they met perfectly in the middle, the one car would have traveled 150, the other car would have traveled 150. So either way, their total distance traveled is going to be 300. Alright. So now we want to use some set up some equations. So we have 1.5 hours, or the rate, h times 1.5, that's how far the Houston car traveled. 1.5 times d, that's how far the Dallas car traveled. Adding those two together is going to have to give us 300, their total distance traveled. So we can set up an equation that shows that to start. We have 1.5 h, it's going to be how far the Houston car traveled. 1.5 times d, that's going to be the distance the Dallas car traveled. Together, when we add them up, that has to give us 300. And then the other equation we know from this problem is that the car that left Houston, it's towards Dallas, is traveling 15 miles per hour faster than the other car. Okay? So we know that the Houston car's speed, which we're using h to represent, is going to equal the Dallas car's speed plus an additional 15. Okay? Since it is going 15 miles per hour faster. So how these two equations are set up, it's we already have one of the equations solved for h. That makes substitution a good method to use. Okay. So back to that method, we take whatever h is solved, whatever h is equivalent to, d plus 15, and we want to take that and replace h with that expression in the other equation. So we're going to take d plus 15 and replace h with that d plus 15. So coming over here, I'm going to start writing this. We have 1.5 h, but we're replacing h with d plus 15 plus 1.5 d from the original equation, and then equals 300. Now we have an equation that only involves the variable d. We can solve this for d. So we want to start by distributing the 1.5 in. And doing this, we get 1.5d plus 1.5 times 15 is going to give us 22.5 plus another 1.5d that was already in the problem equals 300. Okay. Now we can combine our like terms. The 1.5d plus another 1.5d is going to give us 3d. And just to save some space here, well, now we can write that. 3d plus the 22.5 equals 300. Subtract 22.5 from both sides. We end up getting 3d equals 277.5. and then dividing on both sides by 3. I have to cram it in here. This tells us that D, the speed that the Dallas car was traveling, dividing